Welcome everyone, and thank you for joining us. My name is Angela. I'd like to welcome you to our webinar, Using Digital Twins to Accelerate R&D and New Process Development. Before we get started, I'd like to go over a few logistical details. To start off, this is what the 23 webinar platform should look like to you. On the left-hand side, you'll see the screen, and on the right-hand side is the panel where you can ask questions to our presenters. If you're joining us from a mobile phone, you should see a similar interface, but the questions box will be at the bottom and the screen at the top. I do encourage you to submit questions for our presenters during the webinar, so we'll be ready to answer all of them at the end for the Q&A. We will also be doing a few polls with the audience throughout the webinar, so just be ready for those. Okay, and to introduce our speakers for today, our speakers include Toby Howlett, our pre-sales solution consultant at Siemens, Stepan Spatenka, head of the catalytic reactors practice at Siemens, Shaheen Gudarznia, research engineer at Nova Chemicals, Qingling Huang, product developer at Siemens, Reza Hagpana, research scientist at Dow, and Alessio Centenio, senior consultant engineer at Siemens. Now, with those introductions out of the way, I'm going to go ahead and pass it to our first speaker, Toby, to go ahead and get started.
Great. Thank you, Angela. Nice to meet everyone. Thank you for joining. My name is Toby. I've been working at Siemens for about 5 years now, focusing on the chemical industry with a tool called GPROMS, which is a digital twin advanced process modeling tool. So I'm going to just give a brief introduction to just give some context to this webinar. I'll try not to spend too long on this because we do have quite a lot to cover. But just to kick us off, I'd like to remind us of some current trends that are dominating the chemical industries, just to understand how we can navigate around those and how digital technologies can play a role in that. So starting with the end market growth, I guess despite general underperformance of the chemical market recently, in 2024, we've seen quite strong outlook for CapEx projects, particularly related to green technology development. And these are usually backed by the government in emerging areas such as battery manufacturing, ammonia storage and cracking facilities, and biofuels, to name a few. It's just really good. It's creating new opportunities and demand. And they're also quite fast-moving areas. So usually where CapEx is approved in these cases, it moves quite quickly, which means the reduction of those timelines and accelerating development is even more critical. Moving on to shifting demand, 2025, I think we'll continue to see that volatility in price and demand due to political situations and rise in energy prices. And the chemical sector will need to adapt, particularly as the energy transition accelerates. So responsiveness, flexibility are key here. I mentioned a little bit around sustainability earlier, but not only are these niche renewable growth markets emerging, but I think there's a pressure on the chemical industry as a whole, which is being pushed to decarbonisation by regulatory, scientific and public pressures as the impacts of climate change grow more apparent, and they're obviously going to continue to do so. So not only does this mean accelerating new processes to market, but also reducing carbon emissions of existing plants wherever possible. So for example, petrochemical sites are now being targeted for retrofitting of carbon capture systems or hydrogen plants to reduce their carbon footprint. Then coming on to digital transformation, in general, the ability of digital technologies to transform the chemical industry is still relatively unexplored in some areas. However, obviously these tools are evolving in line with net zero strategies and in part with advancements in AI. And the industry does predict uptake in digital technologies going forward with a year-on-year growth from 2025 onwards. And lastly, coming to customer centricity, customer expectations and behaviors have changed dramatically through the last decade, possibly accelerated by COVID-19, where chemical businesses today are now expected to meet the customer's needs and expectations at every interaction in return for customer loyalty. So again, flexibility and responsiveness are key in staying a step ahead of the competition in this case. So what do chemical companies need to do as a result of this? Some of the implications we believe as a result of these challenges are as follows. So firstly, we have the need to innovate through optimal design of new sustainable processes. We also have the need to respond quickly to changes in market conditions. So I think these 2 points here are very much focused on new process development and being flexible and responsive, more proactive. Whereas maximizing performance of operations and increasing sustainability by reducing energy requirements, waste and pollutants are more focused on working with what you already have and looking at reducing your current emissions and costs on your current processes. So these last two we'll be focusing on in our second webinar, which we'll mention at the end of this, so more on that to come. But for the focus of this webinar, we're going to focus on these first two, which are going to be more focused around the R&D and new process development. So as a solution to these challenges, companies are turning to digitalization strategies. And obviously these cover a huge variety of use cases. But I think what's critical is really how do we overcome these challenges and achieve these objectives in the short term? So do we have any proven technologies that can provide value to chemical companies in the R&D and design spaces right now? Before we go into some of the ways which digitalization can help there, I just want to quickly introduce the concept of a digital twin. I'm imagining many here are already familiar with this, but in case you're not, here's a quick video demonstration just to get us on the same page. So you can see here, this is GPROMS, which is an advanced process modeling environment which Siemens provides. Essentially a toolbox that gives engineers and chemical companies the necessary equipment to accelerate innovation and overcome these challenges. So here you can see the model environment, complete with a set of model libraries, which we provide, which capture the physics-based phenomena in the form of first principle equations for different unit operations in your processes. So this can include, your equipment configuration, reactions, heat and mass transfer, property predictions, and the list goes on. And so these can be dragged and dropped into your flow sheet to create your chemical processes in digital form, such as this one for a cumene plant that we're showing on the screen here. And this will consist of some source units, reactors, distillation columns, just representing the end-to-end process. And so you can see we're filling in those specifications through the pre-configured dialog boxes there, and the flowsheet can then be used to perform steady state and dynamic simulations, as well as other model-based activities within the same integrated environment, such as optimization, design space analysis, and so on. And the kind of results that you're seeing here can give engineers the information they otherwise might not be able to access or accurately predict, such as mass energy balance data, as well as detailed temperature and pressure profiles, or in the case of some more detailed model libraries, microscale results. So this model can then be used throughout the process lifecycle for different applications, maybe starting at conceptual design and then detailed engineering before being used to operation support and with potential to be deployed online and integrated with real-time data. But again, more on that application in our second webinar. So just taking a closer look at some of the collections of our off-the-shelf libraries that we just saw in the last video, I'd say these can typically be split into 3 different areas. So starting with our standard model libraries, these cover the traditional and more commonly used unit operations in the chemical and process industries. So operations such as reactors, heat exchangers, pipes, pumps, distillation columns, all the usual stuff you'd expect to find in an advanced process modeling environment. And then secondly, we have the advanced model libraries, which are of slightly higher fidelity and provide a lot more detail to varying degrees that are specific to that unit operation. Our speakers are going to cover some of these in a bit more detail later in the webinar. And then lastly, we have the domain-specific model libraries, which are used for specific application areas in certain industries. So they're not typically generally applicable. An example there might be polymerization or process safety model libraries. The good thing is all these model libraries are usually able to be integrated with each other and can be used in steady state and dynamic scenarios. Okay, so looking specifically at R&D and engineering design, I'm just going to briefly highlight some of the proven applications or use cases I was mentioning earlier that GPROMS allows, and some of these will be covered in more detail later. So first is that ability to incorporate experimental lab data using our robust model validation workflow, improving user confidence in the model by aligning to that experimental data. We have outstanding design space capabilities to rapidly explore the process decision space at any point in the life cycle. So this could be in the R&D space or the engineering design. We also have very strong optimization solvers, which are able to handle large, complex flow sheets with many decision variables, which allows you to assess downstream decisions on the upstream characteristics and vice versa. And I obviously have mentioned these advanced model libraries, which are developed by our subject matter experts, who are at the forefront of their fields, which helps incorporate new technology advancements as soon as they come in. And then the GPROMS platform allows easier and faster scale up from laboratory to pilot plant, and then finally to production plant, while maintaining that core technology, information, and the associated parameters with the technology. And then finally, we've performed various projects with GPROMS and computational fluid dynamics in hybrid to give a comprehensive detail on the flow patterns in combination with information like the reaction data. So that's all from my side. I hope that gives a good broad overview of the different applications. I'll now pass on to Stepan, who's going to give an overview of the catalytic reactors model library. Thank you.
Hi, everyone. My name is Stepan Spatenka, and I'm head of our catalytic reactor practice as part of Competence Center for Process Modeling. And the key responsibility of our practice is to development and maintenance of advanced model libraries for fixed bed and trickle bed catalytic reactors, supporting our users as well as delivering some services related to these areas. Let me start with briefly introducing the scope of these libraries. So they allow users to model tubular reactors in axial flow reactors, in starting with adiabatic reactors, single or multi-stage, or you can model a single tube or multi-tubular reactor with a single or mixed catalyst. Or you can configure radial flow reactors, adiabatic or cooled, or you can even model moving bed reactor with the same libraries. All these models are highly customizable. You can provide your own reaction kinetics, bed properties, physical properties, the activation models. The typical challenges addressed by these libraries in reactor design and operations is typical scale-up, how to maintain performance over scales from laboratory to commercial plant. And also hotspot eliminations by designing a reactor internals and cooling systems, and also catalyst deactivation or maintenance of catalyst deactivation by optimizing the reactor operation over the catalyst lifetime, and also how to integrate the reactor with the rest of the process, considering recycles, separation difficulties, or cost of energy. We approach this with multi-scale models, so we do consider phenomena taking place in the catalyst pellets and the micrometer scales. These are mainly the reactions, heat and mass transfer, internal heat and mass transfer phenomena. Then, of course, in the tube as well, which is mainly the bed heat and mass transfer phenomena. And then there are a number of decisions at reactor unit size. And this is, of course, because what happens inside the pellets actually affects the performance and optimal design of the actual reactor units. And therefore, we need to consider all these scales. And only such models can be really used for design and operation applications. The reactor libraries are relatively flexible in terms of configuration. They allow you to specify different tube sections or different tube configurations, starting with a stack bed like catalyst layering, integrated reactors, tube-in-tube arrangements. They also allow you to specify different details in the tube that you want to consider, one-dimensional, two-dimensional models, and also allow you to define more different catalysts in the same reactor, same tube, up to 3 different catalyst types. Additionally, on the pellet options, you can define various pellet types, starting from uniformly distributed activity to axial types of pellet, and different shapes, like a spherical, cylindrical, ring type, or hollow cylinder, or multiple hollow cylinder type of pellets. And you can also consider different details inside the palette, starting from simple lumped models for the catalyst to fully distributed multi-component diffusion reaction systems. This flexibility and also the modularity of the libraries actually help to de-risk the actual scale-up of the reactor design, where the same building block, the catalyst tube section, is used to build lab reactor models as well as a tube or power plant reactor models. In this example, it's a single tube with a cooling jacket arrangements. And to configure the industrial multi-tube reactor model, there's a number of decisions on the tube side, like catalyst layering, tube dimensions, number of tubes, and on the shell side, like a number of buffers and type of buffers that you want to use. All this is incorporated in the models. However, there are some phenomena that are not easily predicted from first principles, and there is typically some work required, and that's the kinetic parameters for reactions at the activation. These are coming from different catalyst manufacturers, and we don't offer a library of such kinetic models. And properties of the catalyst bed, mainly the heat transfer characteristics, which are difficult to predict to high accuracy due to the bed and pellet non-idealities. However, for all this, we have working examples based on literature, and also industrial standard correlations for most of the phenomena, which are used for getting good initial predictions. However, whenever more validation is required, GPROMS has model validation features as a standard features, and they allow users to compile data from lab or pilot scale or even industrial scale, and use them for model validation. So that was briefly introduction to our capabilities for catalytic reactors modeling, or our approaches to catalytic reactor modeling. And next, let me hand over to our guest speaker, Shaheen Gudarsnia, who will talk about how they apply our libraries for their reactor design applications. Thank you.
Thank you, Stefan. Hello, everyone. Welcome to this presentation. Just a brief, quick introduction. My name is Shaheen Gudarsnia. As it was mentioned, I'm a research engineer at Nova Chemical Corporation. I've been with the company for the past 10 years, and my background is PhD in heterogeneous catalysis. Now, without further ado, I have one slide, and I'll go through it if you move to the next slide, Stefan. So I want to first start with the challenge we were facing in a case study that I want to present today. So in general, scaling up reaction kinetics for a catalytic process from a lab scale unit to a pilot scale unit is a crucial step in evaluating commercial feasibility of a process. Now, a common challenge petrochemical industries typically face is the high piloting cost and time-consuming nature of this activity. So unlike the traditional approach, this is the solution we took. We rely on which relies on a high number of experimentation at the pilot scale. In this particular case study, we used the high fidelity predictive GPROM based model, which I refer to as a digital twin, combined with an appropriate design of experiment at the lab scale. This approach led into development of an intrinsic kinetic model at the mentioned scale. Now, following that, using the design of experiment at the pilot scale, which, as you can see in the screenshot, the scale-up factor was 2,500 times. up to 2,500 times. Catalyst bed correction factors for transfer and hydraulic phenomena were developed. This resulted in development of the kinetic package, which consisted of intrinsic kinetic model plus the catalyst bed correction factors. Now, using the kinetic package, subsequently, the kinetic model package was capable of predicting the performance at the pilot scale. Now, like any other good engineer, you need to put index to measure your success and make sure the validation of the kinetic at the pilot and lab scale has happened. So in this case, we developed parity plots at both lab scale as well as the kinetic scale. And we use catalyst performance indexed by conversion of the reactant as well as the selectivity towards value product as our indexes. And the threshold value for success was in this parity plot was to remain below plus minus 20% relative error or plus minus 5% absolute error. And in both scales, the mentioned criteria were satisfied. Now, let's get to the benefits. Using this strategy combined with the high-fidelity GPROM digital twin tool, we were able to, in this case study, to reduce the number of pilot experiments by approximately 50%, leading into significant reduction of cost and time saving. And so that ended up being a great success for us. And with that, I pass it back to Stefan.
Perfect. So I think now we can hold here for the first poll that we'd like to ask the audience before we move on. So I'm going to go ahead and start the poll now, which you guys should see. If you can just take a few seconds to respond. The poll is, how relevant was this customer story to the issues your company is facing? Okay, perfect. Thank you, guys. And now we're going to go ahead and move on to Qingling. Ooh, Qingling, it looks like you're muted. If you can just unmute yourself.
Oh, sorry.
Perfect.
Hello,
Yep.
everyone. Yeah, my name is Qingling. My background is in chemical engineering and in the area of absorption and process modeling. My current job role at Siemens is develop and maintain GPROM's process absorption, ion changing, and membrane products. GPROM's process fluid separation model library include distillation, gas liquid contactor, absorption, ion changing, and membrane. Today, I will focus on absorption library. Absorption separation is a complicated process. Fluid composition, flow temperature, and pressure can change in axial or radial position, or even both in the absorption column. And different transport resistance can dominate when sorbate is absorbed into the adsorbent. And the absorption separation is a dynamic process. The operating procedure is complex. One operating cycle can contain many steps. For instance, adsorption, pressure equalization, blowdown, purge, and pressurization. And the flow can be co-current or counter-current in a column. This causes major discontinuities and pose a challenge in the numerical solution. Adsorption modeling tool is often used for process improvement. For instance, optimization of equipment size or operating conditions. It should be noted that simulation results are only meaningful at cyclic steady state. And we know simulation may take tens or hundreds of cycles to reach cyclic steady state. Therefore, it is essential to have an adsorption tool that can solve the model robustly and efficiently. And GPROMS has already been a global leading tool in adsorption R&D. gPROMS process adsorption library has advanced modeling capability. The model was developed based on the first principle mass, energy, and momentum balance equations. It is a one-dimensional model with flow either in axial or radial direction. The column can handle with packed adsorbent or structured adsorbent. And different adsorption kinetics are also included in the model, and a variety of standard adsorption isotope model has also been included. For example, Langmuir-Flanders ideal adsorption solution theory. And the adsorption model can be used to model multi-bed, pressure, or temperature swing adsorption process. The schedule model is used to model the complex operating procedures. For instance, open or closed valve, set feed flow rate, temperature, or step time, and a number of cycles. gPROMS process adsorption library is tailored for easy customization and calibration. The library provides a list of custom templates. The user can easily implement their own models, such as adsorption isotope, adsorption kinetics, etc. The adsorption model can be validated with lab or plant data using powerful gPROMS model validation technique. For instance, user can extract mass transfer parameters from column dynamic breakthrough profile by fitting data with model prediction result. gPROMS process adsorption library is aimed to improve model accuracy and efficiency. For multiple PSA simulation, the computational speed can be very slow. The library provides self-iterating bed option, which is used to represent the multiple PSA operation. This significantly speeds up simulation and save time to reach cyclic steady state. Adsorption library provides both finite difference and finite volume methods. For finite volume method, we have first order upwind, third order, and fifth order Vino numerical scheme. The high order Vino method reduces numerical dispersion and improve accuracy. Finally, I would like to mention that we keep updating our adsorption library, and we value users' feedback and improve our library. For instance, Lisa from Dow proposed to have Vino finite volume method in adsorption library. We implemented it in the model, and this new feature will be in the coming release of gPROMS process 2024. Now I'd like to invite Lisa to present.
Thank you very much, and hello everyone. I'm Reza Hakpana. I'm a process research scientist at Dow, and today I'm going to talk about optimization of carbon adsorption processes for VOCs removal from airstream at Dow using gPROMS process. I would also want to acknowledge the contribution of the folks who are listed here, and I want to also thank the Siemens team for giving me this opportunity. Next slide, please. So removal of volatile organic compounds, VOCs, from industrial air emission streams is carefully considered at Dow. And it is quite common to use fixed bed adsorption using activated carbon to remove VOCs from the air. We use gPROMS process adsorption library to simulate and optimize more than 5 different carbon beds at Dow. The user-friendly interface offered by gPROMS process adsorption library provided the opportunity for us to quickly evaluate different competitive adsorption isotherms, such as dual-side Langmuir isotherm, and also ideal adsorption solution model, IAS. Next slide, please. We also evaluated a novel approach to use symbolic regression tools such as data modeler to fit single component equilibrium data, and then use the isotherm model in the IAS inside gPROMS for predicting multi-component adsorption equilibrium system. So data modeler learns both the model structure and parameters to model a data set using genetic programming. So unlike the traditional approach where you fix the isotherm equation and fit the parameters in the isotherm, you will use data modeler or symbolic regression tools to come up with the isotherm equation for you using the data. And data modelers share the result in terms of accuracy versus complexity, such as the figure on the top right corner. So each point in this figure corresponds to a unique symbolic regression model or the isotherm model. And based on the desired accuracy and complexity, you can pick any points on the Pareto curve, which is the outer surface of this envelope. And then you can use that inside GPROMs and use that with IIS model. So here I'm going to share one example where we use this methodology inside GPROM's adsorption library. So if you could go to the next slide, Chinlin. Yeah, thank you. So we try to model, as I said, and optimize multiple carbon bed system in DAO. And here I'm showing one example where we had ethylbenzene, IPA, and xylene in our vent stream, and we were trying to capture those using the carbon bed. And we had also water in the system, so we used data modeler to come up with the water isotherm equation, which is shown here. And for the VOCs, we use a dual-side Langmuir isotherm. Then once we fitted the unary equilibrium data using these model, we were quickly able to evaluate IIS inside GPROMs because of the user-friendly of this program. We were able to simulate multiple cases and identify the saturation point and the breakthrough point for this multi-component system very quickly. With that, I will hand it over to Chinling. Thank you so much for your attention.
All right, so before we move on, we're going to go ahead and start our second poll. So the second poll, how relevant was this customer story to the issues your company is facing? If you can just take a few seconds. All right, great. And now we're going to go ahead and go to our next speaker, Alessio.
Hello, thank you. Hello, everyone. Alessio here. I'm a senior consultant engineer at Siemens, and I work in the electrochemical reactor practice as a senior consultant and developer of the electrochemical reactor models. So I will be introducing today to you the ECR models and see how they are usually used in industry. What you see here is the actual representation of the flow sheet model of the electrochemical reactor. In this case, it's an electrochemical stack in GPROMs. So what is actually inside this model that you see here? Now, if we go in detail, basically, the GPROMs model, the stack model has a series of tabs for the user to configure them. In this case, the stack model, as you can see, starting from the design tab, lets the user define, for example, the number of stack, number of cells inside each stack, and then basically the dimension of the active area of your stack. If we move, for example, to the operations tab, we can see that here the user can decide which kind of operation, like to run the stack. So it can be either specifying current density, current, voltage, or power. If we move to the dynamics tab, you can see that basically this GPROMs model can be switched between dynamic on or off, which are very easy, I would say, setting menu here. Another interesting thing could be the definition of the phases or the phase dynamics that you can have inside your stack. In this case, we are seeing the anode phase dynamics tab, in which the user can basically specify which phase will be inside that, basically the anode part of the stack. Then you can see, for example, for the anode catalyst, all the specification that the user can give to basically characterize or to specify his particular anode catalyst. And then finally, if we move into the electrochemistry, where the user can specify for example, in this case, the anode reaction is the oxygen evolution reaction with the associated stoichiometry and kinetic parameters. And also to finish with the membrane properties, where you can also specify the user can specify the parameters related to the transport and geometry of the membrane. Something to keep basically in mind is that whenever a user drag and drop a model from the palette into GPROMS and double click for the first time on the model, the configuration tab that you see here, there will be already pre-populated. So these are not going to be empty. So every tab, every specification is pre-populated with literature, I would say default values. All right, after this quick overview, now let's go actually into the model characteristic. So it's a multi-phase model. They can be run in steady state to dynamic model, and we have different, I would say, level of fidelity. So we have 0D, 1D, and 2D model. These models are based on first principle mass, energy, momentum, and charge balances. So this basically gives a high fidelity of the model within a wide range of operating conditions. For the electrochemistry kinetics model, we use the Butler-Volmer approach. And also we provide within the model built-in literature. As I was saying before, what you find there as the first time you open the model and the dialog box of the model are usual literature values. And also we also provide basically custom modeling templates for the user to implement their own correlation, which they might want to keep within themselves as IP. Okay, so what are the building blocks of the model? Probably looking at the specification tabs of the graphic user interface, you can understand that the model follows the kind of geometrical structure of an electrochemical stack. So you will find your bipolar plates, your flow regions, gas diffusion layers, which can be included or not just by a simple switch, because we know that some basically stack have them and some don't have. Then your catalyst layer and in membrane layer, and then on top of this you can also have cooling. So you can also include the model of the cooling inside your stack. Now, with this kind of model, especially with for example, with the 2D model, the really user can go into the detail of what's really happening inside each layer of the stack. So, for example, in this case, you can see the half cell reaction rate at the anode catalyst layer and how it evolves across the thickness of the layer and along I would say the length, basically along the flow of the space of the channel. Another example is the temperature. Then we can have, for example, the ionic potential. And then if we move actually into the flow channels, you can, for example, here have an example of how your phase fraction of vapor evolves along the length of the channel and throughout the simulation time. As I mentioned before, regarding the custom correlation and what the user can implement, these are some screenshots related to a demo that we have to present how, for example, a user can implement their own equation into a custom template in order to, for example, in this case, to perform degradation data. So we know that degradation data in this case are really I would say high value data. So probably the manufacturer or the user that want to keep them with the information with them. So this is what we do. So to provide custom templates, and this is an example of validation of your degradation data for a different age stack together with experimental data and the model prediction. Okay, so once basically we have defined the ECR model in quite detail, we can move into actually how to develop your digital twin with this kind of model in GPROMS. So let's say you have some experimental data which can be run by you in your lab, or you can receive them as, I don't know, performance curve from a manufacturer. Then you would use your data and feed them into gPROMS, and then validate your stack model using the built-in model validation entity within gPROMS. And you will create the first digital twin of your stack. And then you can start basically analyzing the performance of your stack. So you can study transient behavior or explore decision space, basically using other in-house or built-in tools within gPROMS to study the performance of your stack. And then eventually you can incorporate your stack in a bigger system. So considering, for example, a full electrolyzer system with separation, cooling, compression, and storage. And in this case, study the performance of your actual system. So once you develop your electrolyzer system, you can, within gPROMS, incorporate that together with other libraries and study the actual bigger system. So like in this case, we have the detailed electrolyzer model in this section. Then we are providing a fluctuating energy input with a battery as well. We have the hydrogen storage. You can see that the hydrogen production is now coupled with the ammonia reactor. So you can also perform and study the coupling with the detailed reactor model to produce ammonia. You can input controller to basically control the operation of the electrolyzer, of the entire system itself, and so on. Okay, so we'll move into now some of the relevant user application from industry. So one of them is Protium. Protium used their gPROMS to, first of all, to build a digital twin of their electrolyzer, actually of their, not just the electrolyzer, but the system, the complete system itself. And they started with using the offline gPROMS process simulation tool. And then they moved into a real-time application in which they use the gPROMS digital application tool. In this case, they really took advantage of the soft sensing to measure performance, basically to calculate performance of the stack based on real-time inputs, and actually to optimize the schedule and the production, basically a production schedule of the electrolyzer based on forecast demand for the following weeks. Another industry success story was is the ongoing EFIRA project, which is based on the creation of the digital twin of our 30 megawatts electrolysis plant to supply green hydrogen to motor oil in Greece. And I would say the project is quite similar to what Protium is doing. So at the moment, the consortium is using gPROMS as an offline calculation tool to perform design calculation and basically optimize the layout of the system. And the next step is to actually move into a real-time digital application in which the user can visualize through a dashboard, real-time dashboard, the operation, and eventually run real-time optimization and change the schedule of operation of the plant. I think with this, that's all from me. Thank you for the attention, and I can give this back to Angela. Yeah, thank you.
Thanks, Alessio. So we're just going to stop here for 1 second for our third poll, which I'm going to start right now. So the third poll, how relevant were these two customer stories to the issues your company is facing? You can just take a minute. All right, thanks everyone. And now back over to Toby.
Yep, great. Thank you, Angela. So I just want to summarize really what we've seen in this presentation. So to start, we explored some of the challenges that we're facing in the chemical industries and looking at some of the implications of that specifically in the R&D space, and then some of the applications GPROMs can provide to help resolve these. We've also provided a look at a selection of case studies from customers showcasing the benefits of GPROMs in these different industry areas, backed by several customer speakers. So yeah, thank you to the customer speakers who presented here. It was very interesting. And then additionally, we've also had our subject matter experts from the competence centers showcasing our advanced model libraries and their different features. So hopefully, I think what you can get from this is quite a broad variety of different applications and model libraries that GPROMs is appropriate for. And so, yeah, I think in general, if you're interested in any of these at all, then please do feel free to get in touch, and we can go into more detail into some of these libraries. But as a reminder of some of those applications in the R&D and design space, we've got some of those at the bottom of the slide here. We'll be going into applications in the operations space in our next webinar. Angela, I think you have a slide on that, right? That you want to share. Yeah. So maybe it's a good point to just mention that. We'll be hosting that on the 27th of November, and that will cover applications in the operations space.
Perfect. So then I'll take it and just do the last poll of the day. So I'm going to start that now for you guys. So would you like to speak to an expert in more detail about the solutions presented today? If you can just take a minute. All right, perfect. And so as Toby did mention, we will be having a second webinar on the 27th. And this webinar is with guest speakers from Clariant, SK Innovation, and Immaterial. After the webinar, you will receive a few post-webinar emails with the recording, as well as the link where you can go ahead and register, but we will follow up with you all in an email that will go directly to the registration page for you guys as well. Okay, so with that, then I think we can go ahead and begin the Q&A. So for the Q&A, we'll all go ahead and come on camera for you guys so you can see us a little bit here. Perfect. All right, so then I think, oh, Stepan, it looks like you're still, we can't see you there. Perfect. All right, so then let's go ahead and get to the Q&A. So we have a few questions so far. So maybe the first question here, what is the advantage of GPROMs over the other commercially available software like AspenTech and Aviva?
Yeah, I can take a stab at this one. Feel free, Stepan, Xingling, and Alessia to jump in here. I think one of the core advantages is a coherent product suite that spans from the R&D to the operations. So you've got the GPROMs desktop software, which provides that digital twin offline analysis in the R&D and design space, and also in engineering support. But then we have a platform called the Digital Applications Platform, which is built to integrate that digital twin with real-time online data, also provided by Siemens, which can form obviously a holistic product suite across the life cycle. So I think that's really important, alongside also obviously Siemens's other products. So I think that's a key one for me. Also, the fact that it's an integrated modeling environment, so you can perform dynamic simulations within the same platform as your design space analysis, and again integrating that experimental data. All these different features are encompassed within GPROMs' platform as a base. So maybe the other colleagues from Siemens want to jump in on some other unique selling points there.
Yeah, let me comment as well. I would say the applications that we discussed today, either catalytic reactors or absorption model libraries or the electrochemical reactors, you don't really find equivalent to those in tools like Aspen Plus. Yeah, I mean that's the fact. Yeah, these are advanced model libraries, and you can do other great things there, of course. I mean, especially for these applications, I don't think you can find equivalent product in equivalent models in the other tools.
Right, so then maybe the next question. How do you handle uncertainties in model predictions and ensure digital twins like GPROMs remain adaptive and reliable over time in variable, nonlinear processes?
Yeah, I think I can answer that as well. Again, feel free to jump in, anyone. But yeah, that model validation capability, which we talked about, albeit briefly earlier, is definitely helps aid that. So the idea there is to take your experimental data from your lab. Let's take the case of a reactor, for example. You take that lab data from the lab scale reactor, and you use that to validate kinetic parameters within the model. Essentially, what GPROMS is doing there is an optimization to minimize the error between the model predicted values and the experimental values. And it will do that by adjusting this parameter value. So you may start with a good guess from literature or otherwise, and then that will be refined according to the data you have, so you can be confident that your model is predicting what you're observing in reality.
I would add here maybe that today we talked more about R&D applications, but this question was probably more relevant to adaptable models for something which is running, and how the models actually adapts for changes in the process, changes to the equipment, and that's something which will be probably covered more in the next webinar when it's about operation support, where we really the digital twin as such would be really applied or connected to the actual process and self-adapting using other aspects of the GPROMS platform, which we haven't really discussed today. Yeah.
All right, so next question. This is a good one, actually. So how different is GPROMS to other Siemens products such as CIMIT or PCS7? Can it be integrated? And how do you imagine the results would look like? Will it be advantageous or sort of redundant?
Mm-hmm.
Yeah, don't know, Toby, if you want to answer that.
No, let's go ahead.
Yeah, so I've used CIMIT a bit, so I can maybe answer on that. So CIMIT is more an operation training tool for operators. So you can basically run simulation online, stop them anytime, restart them. But from a simulation point of view, it's basically in CIMIT you can't simulate very complex phenomena. So I wouldn't consider it as a kind of competitor to GPROMS. We did actually build a demo in which we integrated CIMIT with GPROMS. So we had a hydrogen plant, and we kept some of the plant section running in CIMIT, and other plants were bypassed by GPROMS, where we basically needed more detailed information from the simulation. So basically the software packages can be integrated, and they are not redundant with each other. Yeah.
Perfect. Okay, so next one, let's see. Is the software also suitable for designing new plants and processes, or rather for optimizing existing processes?
So the point we tried to get across in this presentation is it's both. So GPROMS as a desktop software can also be used as was a focus of this presentation in the R&D and design space for developing new processes. But our next webinar will focus more on the operations side of things, where you're optimizing your current processes. Obviously, you can optimize the design of a new process as well. So yeah, it covers that whole process life cycle.
Okay, and then you might have touched on this a little bit already, but is this software similar to the simulation software of Aspen?
Yeah, I guess as a technology, it's fairly similar in terms of it's an advanced process modeling tool. Like Stepan said, though, you're not going to find model libraries like the catalytic reactor model library or the electrochemical cell reactor library in Aspen. So yeah, there's a bit of a difference there. There's a fundamental concept of the technology. They are similar. They are simulation tools at the end of the day. Yeah.
And we should say, I mean, we talked today more about advanced libraries, but of course, there's library of unit operation models which are actually representing units the same way as you would model them in Aspen. Of course, there are some small details in there and there, but I mean, all the mass and energy balances that you do with Aspen, you can do in GPROMS as well. And for example, I talked about catalytic reactors. On top of the advanced model, not on top of, together with the advanced model libraries, we have also standard reactor libraries, which are like CSTR or equilibrium reactors or simple tubular reactor. But of course, these models, you can use them for flow sheeting, for designing a process, but you cannot use them for designing a reactor, for example. So that was the message trying to pass over at least for the catalytic reactors. So, but these models that you find in Aspen Plus, for example, are there also in GPROM's process.
Okay, and then it looks like we have one final question. What are your sources for substance properties and how many compounds can be found?
Mm-hmm. So yeah, for property predictions, GPROMS has an inbuilt physical property package called GPROMS Properties, and so this has a database. In terms of how many compounds that covers, I mean, we'd have to look in a bit more detail for the actual number there, but it's pretty extensive, I think, is the idea. So yeah, for most traditional compounds, you should be able to find it in there. And then for compounds where it's not available, there's the ability to create your own custom compound with a minimum amount of required data as well. And we can help you along with that as well. So it's a bit more flexible than other physical property packages, maybe. Yeah.
Great. Okay, so I think then we can go ahead and end the Q&A here. I do see there's a few more questions, so we'll go ahead and answer those via email after the webinar is finished. So I want to thank our presenters for joining today. Thank you guys so much, and for everyone else in the audience as well. And we look forward to seeing you in our next webinar in a few weeks. Thanks, everyone.
Thank you.
Thank you.
Thank you.